Hello and welcome. In this video, we're going to talk about how to find the volume if we rotate the area between two curves around an axis that is not the x or the y axis. So let's go ahead and get started. So let's go ahead and look at the region bounded between f of x equals x, x equals 0, x equals 3, and I'm actually going to also add y equals 0 because I want to be talking about a region that is fully bound. So go ahead and pause the video and sketch an axis with each of those lines on there to see what area it is we're talking about. So hopefully you got this little triangle piece of area that is perfectly bounded by f of x equals x, x equals 3, and the line y equals 0. Let's suppose instead of rotating this around the x-axis or the y-axis as we have been doing, let's suppose that we're going to rotate this around the line y equals 3, which actually would be a little bit lower, but you get the idea. If we're going to rotate this around, it would be here. If we're going to rotate this around this line, the first thing I want you to ask yourself is there going to be a gap or is there going to be a hole? Yes, there is, because this space here is not filled in. So thinking about what we did last class or in the last video, we're saying volume is the integral over some bounds. Since we have a hole, we're using the washer method. So we're going to have two different functions that we're squaring. And now let's look at a couple of things. First of all, the line y equals 3 is parallel to the x-axis, which means we're making those rectangles with the x-axis, which means we're going to integrate with respect to x, just as we would if we were rotating around the x-axis. So any line that's parallel to the x-axis, we will also be integrating with respect to x. Any axis that's parallel to the y-axis will be integrating with respect to y. That means that our bounds need to be with respect to x, and we can look at our graph to see that those bounds are going to go from 0 to 3. Now we need to identify what our big and little r values are. So if I look at the axes that I'm rotating from and I go down to the edge of our shaded area here, what is that length? That length is our big radius, and that length is 3. If you actually just measured from the line y equals 3 down to where this graph ends, which is y equals 0, that has a length of 3. So that's going to be our big radius. Our small radius is going to be, we're going to find that from looking at where we get to the top of our area or the closest piece of our shaded area to the line that we're rotating it around. Now in this case, that area under the curve would be 3 minus x. And the reason that it's 3 minus x is because if we just found little r to be x, that would give us this shaded region. But we don't want that shaded region. We want the opposite of that. So we need to have 3 minus x instead of having just r equals x, because we want to go away from that axis. So our second r value is going to be 3 minus x. And now we can go ahead and evaluate that integral. So I really want you to be thinking about, if I draw a line out from the axes that I'm rotating, what is my big R? If I draw a line in from the axes, what is my smaller r? Figure out if we're rotating and going to integrate with respect to x or y, set up, and then evaluate. So if we work this problem through, I'm going to go ahead and simplify inside here. This is going to be 9 minus 9 minus a negative, so plus 6x minus x squared, and we're integrating with respect to x. So this is going to simplify to pi times the integral from 0 to 3 of 6x minus x squared dx. The antiderivative of that is going to be 3x squared minus x to the third over 3, and we're evaluating that from 0 to 3. If we plug in 3, we're going to get 27 minus 9 minus 0. So this is going to be 18 pi units cubed. Now for the rest of this lesson, we're actually going to already have the graph created so that we can really focus on identifying, is it dx or dy? What are the bounds? What are our big R and little r? So let's look at another example. Okay, so here we have the graph of f of x equals x squared and g of x equals 0. It's bounded between 0 and 4. We can see that on our graph. And we're going to rotate it around the line y equals 3. So just like before, the first question I want you to ask yourself is there going to be a hole when I rotate it? Is this a washer problem? And the answer to that question should be yes. This whole area here is not going to exist when we rotate it. It's going to be empty. So that means when we set up our integral, we're going to have our two r values. The next thing I want you to ask yourself is, if we're rotating around the line y equals 3, is that parallel to the x or to the y axis? It's parallel to the x axis, so we are going to rotate with, or we're going to integrate with respect to x, which means our bounds are going to go from 0 to 4 because that's also going to be with respect to x. Now let's look at our r values. If I start at the rotation line and go out to the edge of my area, that's going to give me my big R. In this case, that is 3. If I start at the line of rotation and go down until I hit the bottom piece or the closer piece of the shaded region, I'm going to hit the curve, which is the square root of x. But remember, if I just used, oops, I don't want to write that over here. If I just used the square root of x, that would give me the shaded region connecting the axes. That would give me this area. And we don't want that area, which means we want 3 minus the square root of x to be our area. Now, if we go ahead and simplify inside our integral, this is going to be 9 minus 9 plus 6 times the square root of x plus, minus x dx. So the 9s are going to add to be 0. I'm going to rewrite this as 6 to the power of 1/2 so that it's easier to integrate using the power rule. So if I add 1, this becomes x to the power of 3 over 2, which means I need to multiply by the reciprocal, 2/3. And this is going to be x squared over 2, and we're evaluating from 0 to 4. So 6 times 2 is 12. 12 divided by 3 is 4, and I'm going to go ahead and substitute in 4. Minus 4 squared over 2 minus 0. Now, just as a reminder, 4 to the 3 over 2 is the same thing as the square root of 4 cubed or the square root of 4 cubed. Either way, that's going to give you 8. We're multiplying that 8 by 4, which is going to give us 32. And then 4 squared is 16 minus, or divided by 2 is 8. So this is going to give us 24 pi units cubed. All right, let's look at another example. There's one piece of information I want to add to this problem. It should also say that it is bound around the line x equals 0 so that we know specifically we're talking about this shaded area here. So what I'm going to encourage you to do is go ahead and pause the video and try to just set up the integral. Can you find the bounds? Is it dx or dy? If it's dy, what is the function? Because the function should be in terms of y. What's our big R? What's our little r? So go ahead and pause the video and see if you can work through this on your own, and then unpause the video and see how you did. All right, hopefully you've had some time to look at this. If we are rotating around the line x equals 2, I'm going to go ahead and add that here. If we're rotating around this line, that means we're rotating parallel to the y-axis, which means we need a dy. And there is going to be a gap because the function doesn't go all the way to that axis. So volume is going to be pi times the integral of something squared minus something squared with respect to y. And our bounds are going to be from y equals 0 to y equals 1. Now our r values, our big R, if we go from the curve all the way to the edge of the area, that's going to be 2. And our little r, if we go from the curve to our function, that's going to be 2 minus the value of the function. But right now this function is in terms of x, and we need it to be in terms of y. And we can square root both sides, and since we're only in the positive values for our shaded area, we can just write y equals, or this x equals the square root of y. So our little r is going to be 2 minus the square root of y. So go ahead and pause the video and work through this integration on your own, and then unpause the video and see how you did. So if we work through that integration step by step, we should end up with 13 pi over 6 units cubed. So pause the video if you need to so you can make sure you check those steps, and then we're going to move on to our last example. All right, last problem. Here we have the curve f of x equals x plus 2 and g of x equals x squared, and we're looking at that bounded region. And we are rotating that around the line y equals 4. So what I want you to do is ask yourself the same questions we've been asking ourselves. Is there a hole? Is this a washer method problem? If so, set up the integral. Are we integrating with respect to x or y? Which axes are we parallel to? And then set up the bounds. And then unpause the video and see how you did. All right, hopefully you had time to work through just a little bit of setting this up here. So this is going to have a hole. This is a washer method problem. And since we are rotating around the line y equals 4, which is parallel to the x-axis, we are going to be integrating with respect to x, which means we need our functions to be in terms of x, which they already are, and our bounds in terms of x, so we're going to be looking from -1 to 2. Now we need to talk about our r values. From our curve out to the edge of our function, this is our big R, and it's not fully filled in as it has been on the last view, so it's not just going to be our number. That is actually going up to our curve, our parabola curve. So big R is going to be 4 minus x squared. That's going to give us the length for each part. So we can put that in over here. And then little r is going to be the length from our curve to the bottom, or the closer piece of the shaded region, which is the line x plus 2. So little r is going to be 4 minus x plus 2, which is -x minus 2. Go ahead and pause the video and work through this integration on your own, and then unpause the video and see how you did. So here's the simplified integral before we find the antiderivative. And then let's go ahead and get that antiderivative. And then let's go ahead and evaluate it at our bounds 2 and -1. And then let's clean that up a little bit. And then we can find a common denominator, which is going to be 5. So 33 over 5 plus 15 times 5, which is 75 over 5. And if we combine these, we're going to get 108 pi over 5 units cubed. So key ideas in this section. If we are rotating around an axis that is not the x or y axis, make sure that you know if we're going to integrate with respect to x or y, and that relates to which axes our line that we're rotating around is parallel to. And whatever that is, dx or dy, that relates to our functions and our bounds. I really encourage you to draw those lines going out to your big R and out to your smaller r so that you can figure out what big R and little r are. It's a lot of r's in that sentence. And then go ahead and set up the integral and evaluate it. Go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.